Hello and welcome. So excited to be here today. I'm really pleased you've all made time today to come down and spend some time with me. Headphones? Any headphones on? That's it. Let's go. Let's all put your headphones on. If you're not wearing the headphones, you're not going to hear me. That's it. Are you with me? Thumbs up. Awesome. Well, I'm so glad you came to join me today. Today I'm talking about scalability, serverless scalability unleashed. This is the story of where I started building serverless. We're winding back the clock to when I first started building serverless way back years ago. This quote from James Gilmore, an AWS hero, one of the main benefits of getting started is how easy it is. Serverless is awesome. We can build really quickly. As developers, we can build stuff in simple units of code. We can build more and more of them. And that's what happens. We get instant success. Everything works really, really well. And we go on to the next thing, and the next, and the next, and the next. And before too long, some teams end up here in a big mess. I can see some nods. Big mess, big ball of mud. I'm glad you came today. We're going to go on a journey, a bit of a story about me building out a serverless backend for a large global sporting event held in Melbourne. So we're going to talk through the architecture. We're going to talk through quite a number of things. And by the end of this session, I hope you're going to walk away with the skills and knowledge to be able to apply to your own projects so that you don't make the same mistakes and you can unleash your serverless scalability. We're going to be doing, when you walk away, you're going to be doing less of this as you go forward. And we're going to be doing more of this. And that's what we're hoping for today when you build your serverless solutions after listening to this talk. So where are we going to go today? We're going to talk a little bit about the live scoring system. We're going to talk about the data flows. We're going to talk about the events. We're going to talk about some of the architecture. Then we're going to dig into something that happened while I was on this project, when it all went wrong. And we're going to dig right into that. We'll talk about controlling serverless at scale. So really dig into what do you need to do as an architect to really take care of that scale and make sure that everything goes as planned. We're going to look at taking serverless patterns to production. You know, building serverless is not just about building code and building more code and more code and more code. We need to do it in a structured, planned way. So today is all about architecture. It's about architecture, it's about operations, about planning, all of those things that go into building a solid system that can scale with Lambda in the way that it's built. And finally, we'll do a recap, and that's where I hope you'll all walk away with some solid information to unleash your serverless scalability. So, before we start, we're dealing with live events. So this is event-driven architecture, and it's the very first system that I ever built. I learned how to do serverless here. I built this system in approximately 10 weeks. It was very intense, did a lot of learning along the way. And everything I learned on that project, I find when the first time you do something, you learn the most. And this is where I think I learned the most about serverless. And it's all the information and data that I learned, I've carried forward with me from that day forward in everything that I do. It's foundational knowledge. So today, I'm going to share that all with you today, and you can take that away. Let's get started. So the live scoring system, I'm going to talk through some of the event flows. So live score processing is event-driven. We've got a score processing system in the center. And we've got events coming in from tournament control. We've got schedules. We've got drafts. We've got player names. We've got match setups. We've got locations. They're all coming in as different events from tournament control. We've got a chair umpire. These are people with buttons. They press them, an event comes off. They press it again, another event goes off. They keep pressing it, more events go off. It's all driven by human hands, this system. So it's kind of interesting when you design systems like that. And we'll dig a little bit into that. We've also got statisticians. Again, people with computers and laptops typing stuff in. And events are coming through of all sorts of different stats coming into the score processing system. It takes that and it pushes that into a scoring database. Now, we talked a little bit about how the events are coming in. It's all human-driven. And that's an interesting thing that we need to take into account when we're architecting. Events from systems are quite reliable, they're quite efficient, come in fast. human hands, people make mistakes. So we had to be careful with our database to make sure that we designed the system so that a duplicate event was accepted, because umpires are human. They might give the score to the wrong player. We process that, we show it, we process it. They press it again, they correct it. So we need to make sure that the data model design we had was idempotent, that it didn't have a side effect we didn't like. So we had to make sure that all the events were stored in identified records in the database. Now, with serverless systems, you hear a lot of people talk about idempotency. Who here uses AWS Lambda Power Tools? Yeah, there's an idempotency utility in that. Let's just say it's more deduplication than idempotency. There's different ways of approaching it. You can use code, like Power Tools. That's powerful to add on to something you've already got. Super powerful. Or you can design your system around the fact that you're expecting to get duplicate events, and make sure that you store those in your database in a particular way that you don't destroy the data, but you update it and it's solid and you can use it again. So if you're thinking about idempotency, you can either design your system to deal with that, or you can use code like AWS Lambda Power Tools. So apart from the scoring database, we've got browsers all around the world. We've got customers all around the world, millions of customers coming in through a digital experience API. Companies like to call it digital experience. It's really just a BFF pattern. So it's a back-end for front-end style pattern, talking to the database to pull the score information to provide the initial state in the browser for all the digital experience across both browser and mobile applications. There's an immediate update WebSocket notification component. That's there to do live updates of live pages on the app. So if you're watching a match, you'd see a little tennis ball move from one player to the next as they changed, as the server changed, which I'm quite proud of because I wrote the algorithm for that. That's just me. But all the live updates come through so that as they go. So the front end is loading initial state through the API. WebSocket's receiving all the updates as they go past, so that we're not overloading the API, and it makes complete sense. The other factor of this is the digital experience CMS at the top. That's external. It's an external web system. That's the website that everyone goes to, hosts the web page apps. And it's the component that just is the source of truth for everyone wanting to go to the tournament and see what's going on. Today, I want to focus on this middle section, score processing, digital experience API. That's where the crux of my story is today. I'm going to dig right into that. We'll walk through the process I went in building this. We'll walk through some architectures. We'll talk through some of the decisions we made along the way. And at the end, we'll cover off all those critical decisions. But remember, we don't want to be doing this. We want to really start thinking, when we're building a serverless system, we don't just want to start building. It's so I think most people, when they get their hands on serverless, they just start building because you can. It's fast, it's easy. But you need to start thinking about, how am I going to break my system down? How am I going to think about all the different components and think about all the different patterns that fit into that architecture so that I can really architect this reliably, safely, and make it repeatable for multiple solutions, right? That's what we need to be able to do. So start thinking about breaking it down into smaller pieces. Once you unlock composable architecture in your brain with serverless, you're never going to look back. It just becomes second nature, and it's amazing. It really unlocks what you can do. So, building with patterns. When you think in terms of subsystems, so in this case, we've got score processing, digital experience, obvious sub-patterns. So on the left-hand side with score processing, we're breaking that down. The important thing with our patterns is also we break these down into infrastructure as code, so we can deploy these immediately to the cloud. AWS is making the console really easy to use these days. There's a lot of really cool enhancements. Infrastructure as code with serverless is your friend, whether it's SST, serverless framework, CDK, CloudFormation, whatever you're comfortable with is a fantastic choice. And whatever you're comfortable with is the best choice. There's so many opinions out there. You've got to make up your own mind on that one. So, score processing is a simple event broker. We've got events coming in. So this is a classic event broker pattern. Now, you're going to look at this and go, hang on, there's no event bridge. This experience predates Event Bridge, so I'm not talking about Event Bridge today, but it doesn't matter. Standard event broker pattern, this is an alternative event broker pattern. So we've got a data coming in through API gateway, hitting Lambda, which is doing a little bit of data validation, making sure the packets are properly formatted, it's real data from the right source. And then we're pushing that into an SNS queue, which is then going through to SQS, through subscriptions to Lambda processors. This is a great pattern. Got two different uses of that pattern shown here today. We've got one, which is doing the event processing at the top, pushing that into an SQS queue. Some of the events that came into the system we want to send to the external CMS. So that's how we connected and integrated the separate Webbit CMS to our backend serverless system in AWS. The event processor at the bottom is pushing data through to the scoring database. So it's gathering the score information, it's processing it, and it's pushing those records into that Aurora database in the center of that solution. On the right-hand side, we've got our Digital Experience API block to do the work. Now, it's talking, you'll notice it's also talking to the Aurora database. Now, we started building this out, we started playing with it, we started looking at that going, we really need to start isolating some of our pictures, some of our items. We've got events coming in from the right. We've got even more traffic coming in to the Digital Experience API. So we've got lots of traffic coming in from both ends of our architecture, all hitting centrally that little Aurora database. So we took a decision. We've got our pattern on the left, our event broker pattern. On the right side, we've got a Digital Experience API or a classic BFF pattern with serverless, API gateway to Lambda. We decided to stick a caching mechanism in the center. That live score cache in the center, that's Redis, that's Elasticache. We decided to use that. Redis is fantastic. It's super fast. You know, we were pulling data out of that thing in less than 10 milliseconds, which is awesome. It's great to watch. When you're watching Lambda at scale, doing stuff like that, it's really addictive. Believe me, it's really addictive. This was a while ago, and I'm still very addicted. But we built a classic score caching service at the top. It was run on a timer, from a cron-style timer from CloudWatch. In its kickoff, it just did a very slow pace, slow, steady pace. It would just read stuff from the database, read stuff from the digital CMS experience, and we cached all of the payloads for the different APIs into that Redis cache so that it was immediately available for the front end when it came in at volume and speed. So that's the mechanism we use to speed up the display of scores and other data. And this way, it's also everything's isolated. Our Aurora database has one person writing to it. Our Redis has lots of people reading from it, but only one writing to it. So it's quite calm, which is what we want. So the only other thing we need in this solution, we can't have everyone hitting the API gateway. That's not a really good design from an architectural perspective for a global sporting event, a viral sporting event. At times, we might have 20 million people hitting one page. Everyone's watched that classic match that's been so close, and they're hitting refresh on the stats page, or they're getting the updates on the stats page, and everyone's coming in to look at what's going on. And that's busy. So in this instance, we're driven by a vendor. So we'll use Cloudflare for our caching mechanisms, do CDN caching globally. With this solution, we had approximately 80% of all of our API traffic delivered directly from cache around the world, which is awesome. But that 20% is quite a lot still. But that 20% is based on POPs coming in, so it's kind of like a lot less, not huge. One thing we need to do, in our architecture, we had live notifications through WebSockets. Because we've got Cloudflare, we've got caching in here, we've got CDN caching, we now have delays. We've got delays in what the front end's seeing to what's actually live happening in the system. We designed around that. And when you're designing and architecting a system that's doing things like live eventing, or for live sporting events, you really need to think about, well, how do I make sure the customer gets that immediate experience? So we had to take into effect the caching from the CDN cache. Our API is sent back caching headers. We use caching headers to control what the CDN caches were doing. So at any time, we could actually, if we wanted to, we could adjust what's going on in our APIs, adjust those caching headers, and change the way cache was controlled. That's really important. A lot of people just fix their cache, and they don't have any control later on. So it's really important to think about control. Control is really important when we're architecting systems for scale. We also designed web notifications through the WebSockets. We designed those so that we actually sent the last 3 points for a match through in every single notification, because we estimated there was approximately 45 seconds to 50 seconds of people being out of date. So we made sure that next score, they had every single update they would need. So we had 3 or 4 updates coming through on our WebSocket notifications to make sure that scores were up to date all the time. So when you're building serverless systems, you can build them, you can architect them. We've thought about patterns. We've turned those patterns, we've created them, we've pushed them to the cloud. We need to be able to test it. Now we're dealing with a live scoring event. The data provider that we used on this project, it was based in the US. We could get them to play back tournaments for us, but that wasn't good enough because time zone differences made it really hard. So first thing I did on this project was actually build a scoring simulator to actually simulate the events coming through the system. So when you're building serverless systems, you really need to think about how you're going to test them. And we really need to think about that up front. I didn't write any code until I'd actually built the simulator. We built that with a recording mechanism. So as events came through the API, we could record them. And we used that in the live event, which is awesome because we could redirect those events to our non-prod staging, testing, QA environments. And if any problems happen, we could actually play with those in those non-prod production environments and do work live to triage issues if we found something a bit odd or the data was moving a little bit strange, because humans are entering the data and they sometimes enter strange things. So simulating what you're doing is really important. That drives testing. I mean, the beauty of this is we can actually adjust the speed of our simulations. When we were testing, we actually decided to play back our scoring at 10 times the ordinary speed. Our thinking there was if we could run this in testing in QA and everything was working fine at 10 times back-end speed with front-end working as it does, we'd be fine when we went live. That was our thinking, and we stuck to that. And I think it was a good decision in this particular event. So think about how you're going to move and how you're going to get to production and how you're going to make sure your system is reliable. A lot of it is planning. It's not necessarily technical. Some of it's technical, and we're going to get into some technical stuff in a second. So once you've tested and you're ready to go live, performance testing. How many people performance test their serverless systems today? Show of hands. Nice. That's more than I expected. That's awesome. A lot of people don't. They build quickly. That dopamine hit comes in, they get excited, they're going, yes, this serverless thing works, it's great, it's awesome. And then they go to production and things go a little bit wonky. We're going to talk about that too, what's coming up. So we've got performance testing, we've got people from around the globe, we've got simulated, we've got JMeter coming from multiple places around the world, we're simulating live traffic into the system. And really what we wanted to do here is push the system way beyond where we thought it would go. And we really did try. Which brings us to when it all goes wrong, right? I love talking about when serverless goes wrong. There's a lot to learn from when serverless. I learned a lot on this project just by watching this particular incident. What I didn't know during the first performance test we ran, the people who were running the performance test, they decided that they should take down the CDN cache. And they didn't inform us, they just let us, they didn't even let me know. I had no awareness. What could possibly go wrong, right? Wow. Performance testing is cool, right? Start slow. You start slow and you ramp up. So this is a picture of the main part of the digital experience API architecture that I showed before. So we've got our browsers coming through Cloudflare, CDN cache. Some of those are hitting the API gateway as the cache expires, or a new pop is coming up as traffic is building. And we've got Lambda going off to Redis to pull out the data and score, and that's taking like 10 milliseconds. So they're servicing a lot of traffic. They're probably servicing 10 requests per second, because we all know that Lambda can only service 10 requests per second, right? I think that's the figure. I could get it wrong. So as we get higher volume, Lambda starts to scale up. So we get more Lambda functions. This is what happens when Lambda scales, right? That's what we like. That's what AWS says. That's what Lambda does naturally. And we love that. That's why we build with serverless, right? But then we start getting more and more Lambda connections coming in. And last case Redis, it's getting a little bit hot, but it's fine. It's at this stage, sort of midway, 3/4 of the way through our performance testing, it's behaving really well, right? So everything's humming along, we're looking at it, we're going, this is awesome. I love watching serverless. Then they removed the CDN cache. Let's remove Cloudflare and all the traffic, hit that API gateway, and Lambda started to scale. And if every new Lambda function that comes up is connecting into a connection-oriented system, Redis. But there's more to this story. We've also got the back end. We've got events coming through the back end. We're playing that at 10 times speed. We're playing a live event 10 times speed because we wanted to. We thought that was a good idea. That's also hitting Lambda talking to Redis. So we've also got caching going on. We've got everything going on. And it's also got Lambda building up. So at this point, I'm watching Lambda build up. Lambda's going everywhere. I'm starting to get monitoring alerts. I'm starting to see Lambda scale really high. And I have my QA engineer call me over and go, hey, Michael, I just noticed the score go backwards. I'm like, what? I'm looking at Redis. Redis is hot, but you know, it all goes. The funny thing is, when serverless goes wrong like this, it still seems to function. AWS Lambda is very resilient. It still seems to function. So there's still updates going through. But at this point, a poor little Redis instance hadn't been scaled enough to deal with the fact that the Cloudflare cache had been taken away. And of course, that poor little server, all it's doing is processing new connections. And all those new connections are chewing up memory. They're chewing up CPU. They're taking away file descriptors from the operating system. And pretty soon it's locking out. And all we got now is Lambda trying to connect into Redis, and it's not able to connect. So what happens? Why does this happen? Well, as architects, it happens because we have scalability boundaries. Scalability boundaries exist in every serverless system, and as architects, we need to be aware of those while we're designing our systems, because these are the things that cause Lambda to go really wrong. And those red lines, that's where we are. That's where we have high scale, which is AWS Lambda, meaning something of lower scale. Now, lower scale, people go, when I mention to people I'm talking about Lambda going wrong, they're going, oh, you're going to talk about cyclic loops. And I was like, no, there's more to it than that. You know, in this instance, it was a Redis cache. It's connection-oriented. Anything that's connection-oriented is a scalability boundary. You can treat that as lower volume because there are limits. But you need to, as an architect, we need to understand those limits, those quotas. What's available? How big does it go? Is it big enough? They're the questions we should all be asking. So in this case, I didn't size the Redis cache enough, but certainly a learning experience. Other places we get scalability boundaries. Key ones that I can come up with, anything external API calls. External API calls are a risk to anything you're building in a microservice. I often say to people, my teams, if you've got more than 3 API calls going outbound from your Lambda, you need to look at refactoring your code, right? Because every outbound call is a risk. Every time you call out to an external system, it could be down. Even if it's a microservice that's within your boundary of control, you don't know how resilient that is. If we're not all thinking about resilience, not everything works all the time, right? We know that. Werner Vogel said that a couple of years ago, right? Certainly from this experience of what I had, this is where I learned the most. But like I said, watching Lambda scale, that's addictive. I love it. So when scalability boundaries collide, what happens? We've got Lambda connecting in to our Redis cache. Our duration normally, in normal operation, it's kind of small. It's what we want. It's really quick. 6 milliseconds, I'm in and out. Connected, might take a millisecond. Then I read my data, and I hold that connection open, right? And I just keep reading data, 6 milliseconds time, really fast. It's awesome. But when that duration of your Lambda execution starts to increase, this has an effect in AWS Lambda. It has an effect on concurrency. And concurrency, when we're building at scale is the hardest thing that we need to be aware of and control. And that concurrency is linear. So if your average request per second goes up, your concurrency goes up. If your average request duration in seconds increases, that could be for anything. I've been on corporate projects, enterprise projects, where we've had Lambda in a development environment. We've been forced to put them in VPCs because of enterprise security, which is fine. You know, it's fine these days. Lambda in a VPC, don't be scared. It's actually super fast still. But what they do in enterprise environments, they put other network controls in place. And so what I find in enterprise is often when you deploy, you might set your Lambda duration at 3 seconds. You deploy into the enterprise environment where it's really busy VPC, there's a lot of stuff going on, millions of transactions, lots of traffic being sniffed, traffic being filtered. That all adds delay and latency. And sometimes your actual duration of your Lambdas increases slightly. So you need to be aware of that. You need to be aware of where your durations are going to hit in different environments and plan for that. You can see it's all linear. So anything goes up, your concurrency is going to rise. And that's limited. That's a quota, right? That's a quota on the account for the region. So we need to be aware of that. And when it increases too much, we're going to end up with Lambda being throttled. When you have too many Lambdas running at the same time, AWS Lambda control plane is not going to be able to launch any more instances. It's going to try. All those tries are going to get a 429 denied response, and you won't be able to launch any more Lambdas. So, you know, the other problem you have is if you're doing async invocations to Lambda, it's got 2 more retries natively from the Lambda, right? The Lambda runtime natively by default is going to try to complete your transaction 3 times, which is great. That adds durability and reliability. It really does. But it adds to the storm because it's trying to hit Redis, it's running again and again. So it's really causing more traffic and it just spirals out of control. When one thing starts to throttle, everything else in your account is now throttling. So we don't have one problem when Lambda starts throttling. We have problems in all your microservices. So all of our Lambdas are now throttling, not just in this subsystem, every other subsystem in the account. Now we've got a serious problem. We're looking everywhere. We don't know what to do. Has everyone ever experienced this? A few people, a few nods, yeah? This is crazy scary. What do we do? Projects that I've been on, not this particular one, but other projects I've been on when someone's made a mistake and we've had a Lambda spiral out of control. You often have project managers or technical TAMs go, you know what? I'm going to jump on the phone, I'm going to speed dial my TAM. I'm going to increase the account concurrency. I had a guy come back and go, problem solved. I had the account concurrency increased to 10,000 invocations. Wrong answer. We just started spending 5 times as much on throttled invocations because Lambda consumed those additional 8,000 concurrency and everything was throttling. Yeah? So, you know, you increased from 2,000 to 10,000, you're now spending 5 times as much. How do we get control back in this situation? And that's the tricky thing, right? If this is a live production system, we've got to get control back. How do we go and do that? How do we do? First thing is to do is look for control points in your design, right? Where we're designing and architecting for scale, you really need to think ahead of time about control points. Places where you can stop the processing of a channel or a subsystem within your design. That's golden, because when things are scaling out of control, you need to be able to find the thing that's scaling out of control, and you need to stop it. Because that's the only way you're going to stop this and get everything else to settle down. So using control points to control concurrency is really important. So how do we know what's going wrong, right? How do we find the thing that's going wrong? For Lambda functions, we need to look for the highest concurrency. That's one pointer. Whatever's got the highest concurrency is likely to be the problem. Also, the thing with the highest number of throttles, that's likely to be the problem as well. either of those metrics can help you determine across your functions. You can do searches on those, you can filter, you can actually work that out pretty quickly. You can, if you don't have control points, the only things you can do is to either disable the trigger. That's an internal control point that you haven't necessarily designed for, but Lambda has that built in. Any trigger that triggers the Lambda can actually be deactivated. And that will stop data flowing through that Lambda. And that should eventually allow that Lambda to start scaling back down. And then your account concurrency will return, and everything else should just start working as normal, right? You might have some recovery and overflow to do. You need to work through that, depending on what your system or architecture is doing. That allows us to settle the systems down and be able to recover and move forward and be successful again. But how do we know if it's going to happen? Now, if you go back to a couple of slides before, I was talking about duration. I actually personally, in my humble opinion, the most important metric that you can monitor for AWS Lambda is the duration. I already mentioned before, when you go in enterprise environments, you go to production, they often run slower. I love using CloudWatch anomaly detection on AWS Lambda duration metric, because that uses machine learning to understand what the usual patterns of your Lambda execution is, right? And it will, if it deviates by 1 or 2 standard deviations, it will give you an error. Now, it'll do both ways, either down or up. Like if your traffic is lower than normal, you'll still get a notification. That could be an indication of a problem downstream. But also when it's rising, you'll get an indication before you get to the point where we start throttling. And that's the key here. We want to be able to observe and understand where that fits. So anomaly detection, CloudWatch is great. I love it. I think everybody should just activate that on every Lambda they build. I do. I rate that part of everything I do. So we've seen how Lambda scales out of control. We've seen the architecture we're building here. How do we control serverless at scale? And again, I've mentioned this before, we need to really think about control points. I mentioned that before. We need to make sure, if we've got an event broker pattern, we can make sure we've got an SQ, we can make sure we've got a, we can make sure we've inserted an SQS queue with a control point. And that enables us to turn off the Lambda from being processed. All our events are still captured in the SQS queue. That Lambda settles down, we can go and fix what the problem is. We can deploy something really quickly. That's the great thing about Lambda is we can operate on one particular unit. We can actually fix that triage, fix, and actually then turn back on the SQS queue. One thing we don't often realize is, that's the control point for switching on and off. The other thing we need to look at is we need to look at flow control. So these are just architectural things. The talk really is about architectural thinking. We need to be looking at control points. We need to be looking at flow control. We need to control how fast things flow through our systems. Because at the end of the day, that's going to drive up concurrency. Now, does everyone know about the event source mapping component? It was released a couple of years ago. This now has the capability of setting the maximum concurrency of the Lambda it calls. So you can control through these formulas, you can work out with your TPS what your batch size and max concurrency on the event source mapping needs to be. You can configure your event source mapping to control the flow so that it matches the rate on the other side of whoever you're talking to. So you're never going to go over that. Sure, it's not going to be perfect or ideal. You're still going to have to do some estimating. But at least you know you can actually set your flow control. And to do this, to be able to do this as architects, we need to be thinking about all of our non-functionals. Everyone loves non-functionals, right? We need to understand how many transactions are expecting to go through our system. If you don't understand the volume you're expecting to run through a system, you can't configure your system to process that in a reliable way. And I find in my experience working with a lot of teams, my specialty is system integration. I've been doing that for 25 years. Often when I walk into an enterprise integration project, nobody knows what the volumes are expected to be. How am I supposed to design for that? Know your volumes. If that's the one takeaway you get today, I'm going to stop shouting. I'm going to get on my soapbox in a second. So they're the main thing. They're the main things I want you to think about when you're building systems. So we've talked a lot about architecture and architecting for success. We also talked at the start, we talked about breaking our systems down into subsystems, thinking about those subsystems, breaking those out and creating patterns. Creating patterns and then codifying those using infrastructure as code. And by doing that, we're able to repeat everything we do. But once we also have a pattern, it means that we can just apply that pattern to any other problem we have in the same problem space. So we can actually move faster. And patterns are really important. Really important. And we talk a lot about those. You'll hear serverless DevRels, you hear a lot of other heroes talking about patterns being important. If anyone caught Julian Wood's talk the other day with Ron Eisenberg, they talked a lot about patterns, right? Lots of nods, yeah? Lots of patterns. You can find these on serverlessland.com. Lots of patterns. Instant. Infrastructure as code. You can search by whatever one you use, and you can find a pattern, right? Serverlessland.com is a great resource for learning about common patterns. Learning about common patterns. You can also go to constructs.dev, that's for CDK. That's a place where there's a whole heap of CDK-ready constructs that you can use. And you can pick these things up, and you can just download the GitHub, and you can deploy them to your account, and away you go. This quote is from one of my leads. He's a serverless team lead at Accenture for one of the products that I designed and built. Serverless needs to be experienced. I really believe this, right? You need to experience serverless. And even when we talk about patterns or problems, we often go to the internet to find out ways to solve this. No problem's unique in this world. There's always a solution somewhere. But what we've found in our experience is those patterns and problems and solutions, they're not equal in your particular use case. Every use case in serverless is slightly different. Your system parameters, everything going on in your system is slightly different. So you need to really test out patterns to make sure they work for you in your particular use case, because they might not behave the way you expect. So if you're going to use patterns, often people just YOLO that. They download them, load them up into their account. I've built something really fast. Awesome, let's go build the next thing. Yeah? No. We need to take those patterns, and if you listen to Rand the other day, we need to be talking about blueprints. We need to turn a pattern. A pattern is just a concept, right? It's a usual concept. It's a way of doing things. We need to turn that into a blueprint. And that blueprint needs to take into count a whole lot of things. We need to, I've just grabbed this one. This one I've grabbed, this diagram, straight from serverlessland.com. Standard event broker pattern. API gateway to Lambda to event bridge, firing off into a Lambda, talking to an external service. Now, from what I've shared with you today, you're probably looking at that and going, well, there's probably some things missing from that. Because we've got a scalability boundary, right? As architects, when we're thinking and designing and thinking about our patterns and blueprints, we need to be looking at these things. We need to be looking at scalability boundaries. For a scalability boundary, we need a control point. Because if that goes down, we've got traffic flowing through, we're just going to hit a whole lot of denies and retries, and now we're scaling, and we're scaling up, and we're potentially scaling out of control because of a third-party external service that's gone down or is moving slowly, because that duration is increasing. Again, duration. Duration for AWS Lambda, I think, is its biggest enemy. I actually think that's my opinion. So we need a control point, so we can turn that off. We also need to think about flow control. We need to configure the flow control through SQS so we don't overrun things. But we need to know the transaction volumes. We need to know the rate limits. Then we can actually use the calculations to work out how do we configure this thing so it works every single time, all the time. And then we also need to think about, well, sometimes everyone's looking at that going, where's the DLQ? We need a DLQ, yeah. If something can't be processed, we need to make sure that goes somewhere so we don't block other events coming through the system. And that's really important. So that's what I want you all to take away today is that yes, there's patterns. Yes, they're easy. Yes, we can take them and load them straight up into production. No, we need to think about all of these things as architects, as serverless architects, building for a reliable system that can operate at scale. This is what we need to be thinking about. These are the core things. These are the core things that I learned from that one little Redis cache and everything around it and everything going wrong. These are the key foundational learnings that I pulled away from that project. And they're with me today with everything that I do. And the beauty is DLQ, you can also replay those events once everything's fixed up. So, unleashing your serverless scalability. We've covered a lot of ground today. And I hope you collected some useful strategies that you can take away and think about and apply to your projects as you move forward, building with serverless. This quote from Lee James Gilmore, there's a little bit more to this quote. And one of the biggest downsides of serverless, it's easy to get started with, but it's also how easy it is also a downside. Unleashing your serverless scalability. We need to be thinking about using patterns. Patterns are great. We need to be identifying scalability boundaries. We need to be turning patterns into blueprints. That needs to be part of what we do. And we need to make sure that you're doing performance testing so you can catch these before you get to production. If you don't performance test, you're not performance testing today, you should be. There's some really easy ways of doing that, and I'm happy to talk about that after the talk. We can talk about that if you've got questions. If you do all these things, and you do all these things carefully, and plan it, and understand your transaction volumes, and do your configurations, then you too, with your systems, will be able to unleash your serverless scalability. My name is Michael Wormsley, our neighbor serverless hero. I work for Accenture in the GenWizard group, building internal products for our customers. I build everything serverless, and I love it, enterprise at scale. If you want to learn more, the QR code goes to serverlessdna.com. That's my blogging platform. If you want to learn more about what I've talked about today and other things about services, this is where I blog. I welcome you all in to come and join me on the journey. Reach out with questions. I love hearing about people's struggles because that helps me share information to everybody else to learn. Thank you for joining me today. I hope you enjoyed the presentation. I hope you got something to take away from it. Please complete the session survey in the mobile app. I'd love to hear all your feedback. We value that. Thank you for coming. Appreciate it.